gonna set that in the background today because I'm lazy. So I'm gonna switch the screens over, but we are going to have a math topic today. I'm pretty excited for that. Originally today was supposed to be a guest stream, but there were some scheduling conflicts. We're gonna have Carly on again. You may remember her from the first guest stream ever. But she's actually going to a soccer game today, so we're gonna reschedule that for next month. But I have a cool stream planned for today, so I have the paint screen up, which means you're gonna hear some quiet boodle doops, and we'll get the mouse situation situated. But we can get right into it. So today's topic is going to be, I'm going to pick a slightly larger pen size, the golden ratio. And so this is probably something that you heard about in your algebra classes. It's not something that's emphasized too much just because it just kind of happens, and you don't necessarily need to like derive it or anything, but I'll explain it. So the things I'm going to focus on today are a couple things that its definition. Def is good enough. And then we're going to talk about its visual qualities. And then we might talk about where it shows up. So where? So this may start to sound like a 5-paragraph essay, and that's just a normal format for talk shows in general, so get used to it. Let's talk about the definition. So if you look up on Wikipedia, which I have kindly offered the link for you in the description if you don't believe me, the definition of the golden ratio is some value phi, where that is equal to A over B, and it is also equal to A plus B over A. So this is an equation. We have two unknowns, but we have two equations that are equal to each other. So this, when you solve it out, ends up being equal to about 1.618 and some change. Now, unlike numbers like pi and e, this is not transcendental. So if you don't know what transcendental means, transcendental basically means that there is no real pattern to the number itself, so it can't necessarily be represented by a closed solution. So what that means is phi here, our golden ratio, can actually be represented by a closed solution, and that closed solution is 1 plus the square root of 5 over 2. So that is an exact answer. That is the golden ratio. But if you want to try and remember something, it's about 1.62. That'll get you close enough for most reasonable answers. So one cool thing that I just realized the other day is that there's another way you can define this. So we're gonna get back to these guys, but I'm gonna clean the sheet out so we can get some more writing in here. So one thing that I realized is if you solve the equation x is equal to 1 plus x to the negative 1, you actually get the golden ratio. So this could also be written as x is equal to 1 plus 1 over x, for those of you who don't know what negative powers are. So what this is interesting is that if you take what this means is if you take the golden ratio, which you'll remember is about 1.62, essentially, and then you do 1 over that. So 1 over 1.62 is equal to 0.62, about. So we'll do that. If you are using the actual golden ratio, then it is exactly. So I'm gonna leave that there. So that's just something I found to be cool. It's the only number that does this, because that's the solution to this equation here. So if we look back at the equation that I wrote out, this is basically saying that this number is equal to 1 plus 1 over itself. So if we have 1 over this number, then we have 1 minus the original number because we can move this over to the other side. So that's just something I found that's cool. One way you can figure out what the golden ratio is to solve this is you can actually iterate this. So what you can do is if you take a random number, just pick a random guess, let's say 1341, and you plug this into this equation. So this is our first guess. So this is going to be x0 is equal to 1341. Then we are going to iterate this. So we're going to find out what x1 is equal to. So x1 is equal to 1 plus 1 over x0. So I'm going to actually do this in the calculator, and we're going to see how quickly we can get to the golden ratio, because it happens pretty fast. So we're going to go 1 plus our 1341 to the negative 1, and that will give us an x1 of 1.0007 and some change. So that's going to be our x1. So then we're going to say x2 is equal to is equal to 1 plus 1 over x1. So we'll plug that in. So we're going to go 1 plus our 1.0007 and some change to the negative 1, and we get an answer of 1.9992. I didn't want to round because that would require erasing. So this number that we started with was very far away from the golden ratio, and you can see that we're already pretty close just because of that whole 1 over thing. So if we then take this number and plug it in again, so we can get x3 is equal to 1 plus 1 over x2, and that will give us, so if we go 1 plus negative 1, oh sorry, so 1 plus negative 1 is 0, that's pretty obvious. So our x2 to the negative 1, then our new number is 1.5001, we'll call it 9, and some change. So I'm just going to do that. And so that's even closer than we were, and we should be getting pretty close with the next few ones. So we'll keep going a little bit, but you should be getting the picture here. So we're going to do this again. I'm not going to write this out again. Our next number is 1.66658 and some change, and then our x5 will be 1 plus that to the negative 1, and you get 1.6000 and some change, and then we're going to go over here for x6 is equal to 1 plus this, not squared. We're going to go to the negative 1, and we have 1.62499 and some change. Well, the change is, I rounded, so yeah, I'm going to leave that in 8. And then we'll have our x7 to be 1 plus that to the negative 1, and we are already at 1.61538. And you can see we're pretty close. I'll do one more just to have a nice even number. So we're going to do 1 plus our last one to the negative 1. And now we are at x8 is equal to 1.619045929 and some change. So you can see that even in 8 iterations, we are extremely close to that original number of about 1. I think I have it up here. The number is 1.66180339887 and some change. So now obviously you could you could write a computer program to do this for you, and you would get it very fast. I believe in about 40 iterations, you get pretty damn close. So, and that's from any guess. Even negative numbers, you can plug into this, and it'll bounce back and forth and get back to the right number. I think 0 screws it up because you have to do 1 over that, and then 0 is always a problem. But so I just thought this was cool. I thought about it the other day. I was like, that's interesting that if you do 1 over the golden ratio, you get the golden ratio minus 1. So it's a cool quality. So that's the definition of the golden ratio. And so we're gonna go back, and our next thing we're gonna talk about is the visual qualities. So the visual qualities of the golden ratio of phi. Some people say phi. I disagree. So we are talking about the visual qualities of the golden ratio, and so why this is a cool ratio is that it actually shows up in nature, and we'll get to that in a little bit. But if you actually look down in, I believe, that corner, yes, of my screen, you can see the tail end, or actually the beginning of a little pattern that we tend to associate with the golden ratio. So basically what you can do is you can draw a square, and I'm probably going to draw a pretty bad square. Yeah, I'm going to cut this off so that it's an actual square, and we'll erase that. What you can do is then you can multiply the sides of this. I believe the idea is that you multiply the sides of this by your 0.618, so your extra. So this is like the 1, and then your 0.618 over here, and then you go like that and pretend that's a square, and then what you can do here is you can do the same thing in this direction. So you do a 90-degree turn, and then you do your 1.68, and you actually get back to the edge here. So this is lined up, and we're going to draw a square, and then you can do a 90-degree turn, and you can draw that there, and then you do a 90-degree turn, and you draw that there, and you do a 90-degree turn, you draw that there, and it goes continuously and becomes really small. So I'm going to draw this. I don't know how well pink is going to show up, but we'll see. So I'm going to try to draw the curve that you're seeing down in the corner there. So what it does is it goes and it just barely taps the corner here, and then it arcs and comes through this corner, and then back through this corner, and back through this corner, and so on, and so on. And what you can see is that it is actually a spiral. And now this is the spiral that shows up in a lot of different situations in nature. We might end up just tying in the 2 points here. So if you look at a sunflower, so if we have a sunflower, and I don't know, the flowers have little petals out like this. It's probably a butchered sunflower, but if you look at the actual little seeds, they actually spiral outwards, and that spiral is associated with the golden ratio. It's actually associated with the golden angle, which is associated with the golden ratio. I believe the golden angle, I don't know if it's on this Wikipedia page, but the golden angle is about 130.7-ish, I think. And so basically this is the optimal angle to rotate the next seed or the next petal of a plant, and to have the most area visible. So it's the least coverage while also being compact, and it's just the optimal position in this two-dimensional system. And I'm sure that it also applies into 3 dimensions, but so yeah, you can compact them pretty close together, and you get this natural spiral that comes out. So if you ever look at a plant, you will see this spiral just show up. I believe it shows up in most flowers, but specifically in like cactuses or cacti, I guess, you can see the spirals of the little prickers. and the seeds on sunflowers are usually a pretty big example. But there's also something that might be a little bit more relevant to today's people. So I'm going to draw that out. So if we see a little curved rectangle like this, you might get something that's associated with that. And then we'll draw like this, and like so, and like so. So this is probably something that is relatively familiar to most people. This is, well, it's pretty close to an iPhone screen, but this applies to pretty much every smartphone that's out there on the market. Usually what they go for is a 2/3 ratio, but really what they're talking about is a golden ratio. So if we look at this length and we look at this length and we call this A and we call this B and we say A over B, then this is approximately phi. So that's what's beautiful about an iPhone. I actually have mine here, and I don't know if we can measure this in any way, but I mean we probably could with paint using the pixels. You know, hell, let's try it. So I'm gonna leave the phone case on, and I'm going to do some measuring here. So let me see if I can. We're gonna clean this out. So this is gonna be pretty approximate, but we'll see how this goes. So I'm actually just trying to trace the distance of my phone, and I have a button there, so it's probably gonna be a bump. Oh, that didn't actually write anything. Okay, so I need to be there when I start. So that's kind of off the screen, but you should be able to see it. So if we take this Y value, which is that is 32, and we go down and take this Y value, which at the moment is 818, and we'll take this Y value, and that's going to be 132, and we'll take this Y value, and that's going to be 610 about. So this is obviously going to be approximate, but we're going to subtract 32 from 118 minus 32, so that's going to be 78, or 786, sorry about that. And then we'll go 610 minus our 132, and that's going to be 478. So now if we call this A, and we call this guy B, then we'll go A over B is equal to, drumroll please, 1.64435. So obviously I've made some approximations. There's probably some slight adjustments for size purposes on the iPhone screen, but I think that's pretty neat that we actually have that sort of ratio. Now these are also expanded slightly, but then compressed when I put it into the screen software. So it's probably not exact on the screen, on your screen, but the math should still work out, and it did. So I think that's cool. I'm glad that worked out. I didn't really have that planned. So that's pretty much all we're going to talk about for the golden ratio. If you have any more questions, or if there's any specific examples you'd like me to go over, I'm more than welcome to learn those specific examples, because that's the original purpose of this channel, was to help me learn by teaching other people. So I'm going to switch the mice over, and we'll go do the random drawing, I guess. I might give no, there's nothing really to update on my game, so we'll go to the random drawing. There's a dog barking in the background, but please excuse that. And we will get that switched over, so bear with me. Oh, what am I doing? I need the random drawing, right? So I need to draw. Okay. Okay, so we are here with the random drawing, and we're gonna get this started. I'm gonna switch my pencil back. We'll keep it pretty thick, but not too thick. So you'll see some of the math from earlier, but I'm going to pick the random numbers. So we'll go for the first one. That is going to be 17. We've used that. Our next one is 2, which is laptop. And then our verb is going to be 11. That is sliding. And I'll click it for you guys for the last one. That is going to be 20, which is rich. Okay, so we have a rich laptop that is sliding, but we can try and make this kind of a dual thing because we were talking about the golden ratio, right? So let's think of a rich rock slide kind of idea. So if we have our slant here, and we're going to make this slant approximately 130.7 degrees, and then we'll take our yellow here, and we'll get this to be nice and thick, but we're gonna just imagine that there's a bunch of gold coins here, and so we just have a pile of them. And so I think you get the picture, but I'm just going to kind of finish this out. And so the idea is that we have a laptop that's sliding. So I think that you might have to do some dynamics calculations on this to see if the friction coefficient would be too great for the laptop to begin sliding. But we can assume that it was tossed from the top here. So we'll use the kinematic coefficient of friction, which will give us a little bit more leeway. And because of all these gold coins can move, which will cause some extra sliding and possibly bring the laptop down with it. So we need to also think of a rich laptop. So if we think of an expensive laptop brand, there's one that comes to the top of my head. I know Alienware is pretty expensive, so we'll go ahead and draw that. I am not quite sure what their symbol looks like. I think it's like a weird, like, kind of triangular thing. I don't know. But that looks like an expensive laptop, so I think we're good to go in that department. And so you can see that this laptop is going fast by the trailing winds. Now this is obviously not the most optimal position, so we probably would get some rotation by the laptop. Now that's not the golden spiral, I don't think. I may have accidentally done that, but that kind of just happens with the golden ratio. So the laptop will probably spin around until it is in a different, more aerodynamic position. Now this would be kind of two-dimensional, but I'm going to fudge it a little bit just so you guys can see some more visuals. And then we'll grab our green and our symbol, and then we'll just color in the laptop like so. And we'll go for a little bit more detail so that there's just a little bit like the keys in there. And then maybe the touchpad. But I think that you guys get the idea. We have a very expensive laptop sliding down a rock slide of gold at the golden ratio. So I think that's a rich sliding laptop if I've ever seen one. We're pushing on over 25 minutes now, so I'm going to be signing off. But I will mention that there will not be a tax stream tomorrow. I'll try to get one organized for next weekend, just because we've had this. I think this is the second week that we've missed, and I don't want to get back into another long hiatus from the tax streams. I believe it's Megan's turn next, so that should be pretty easy to set up. I'll just talk with her about getting one set up for next weekend. And other than that, I will see you on Tuesday with a cover and I will hopefully have some more done on my game. I don't think I'm going to get anything done this weekend, but maybe Monday in the afternoon I can get something figured out, and we might have another update in. But until then, I'm going to be signing off. So I'm forgetting I have to switch my mice out in order to do so, but I will keep rambling until we are able to sign off, and now we can sign off. So